Welcome to this hands-on session on fluorescence lifetime imaging in the frequency domain. My name is Gerhard Holst, and here at PCO I'm responsible for the research department. Today I would like to show you how simple it is with our frequency domain fluorescence lifetime imaging system PCL Flim, how simple it is to do FLIM measurements. But before I explain the experimental setup to you, I first would like to refresh your knowledge and your memories about the differences between time domain and frequency domain fluorescence lifetime imaging. Therefore, I would like to show you a short video tutorial that we have created to explain these differences.
Fluorescence Lifetime Imaging, or FLIM, in the time and frequency domain. The differences in fluorescence lifetimes in luminophores can be used as an imaging technique called FLIM. This can be achieved both in the time and the frequency domain. Established examples of time domain equipment are point scanning TCSPC systems. These point scanners count the emission photons in time, allowing you to reconstruct a luminescence decay curve. This makes TCSPC suited for mixed, fast, and weak emission signals. On the downside, the recording speed of the process is slow due to its point scanning nature. One frame of 1,000 times 1,000 pixels can take up to several minutes. And because it depends on single photon counting, it has a limited dynamic range. To prevent under- or overexposing, it has to be tuned for either dim or bright signals. Another kind of time domain FLIM uses a digital image sensor. In this setup, the sample is excited by a period train of rectangular light pulses. Each excitation pulse results in a slightly delayed, weaker emission signal, starting with a sloped rise of the emission intensity giving the rise time, and a decaying emission after the excitation light has been turned off giving the fall time. Repeatedly integrating over the same narrow section of the decay curves leads to the first image. Then, the integration interval is slightly shifted to integrate over another section of the decay curves, giving the second image. This section-wise integration is repeated until the whole decay curve is sampled. The limitation of this approach are the shortest possible exposure times of image sensors. The shortest known exposure time at the release date of this video is about 120 nanoseconds. By the development of a novel, fast, modulatable CMOS image sensor, the QM-FLIM2, the so-called frequency domain method became more attractive. In this frequency domain approach, the intensity of the excitation light is continuously modulated using sine or square waves. The modulation source is the camera, which provides modulation frequencies ranging from 5 kHz up to 40 MHz, as well as the signal for dark gating. Using a sinusoidal excitation waveform, the emission waveform is also a sinusoid with the same frequency. It is delayed in time and shows a decreased amplitude, a decreased constant component, and a decreased modulation depth. By comparison of the excitation and emission sinusoids, the time or phase shift can be determined. The phase angle, phi. Also, the excitation and emission amplitudes, A excitation and A emission, become clear, and the constant components, B excitation and B emission. These characteristic parameters can be determined by sampling and reconstructing the emission signal by a kind of half-wave integration measured at least 4 different phase angles. The first half-period integration is done at a phase angle of 0 degree, giving the image I1. Subsequently, the next half-period corresponds to a phase angle of 180 degree, resulting in image I3. If then the onset of the camera integration is shifted by 90 degrees and the detection is repeated, the first integrated image I2 will correspond to a phase angle of 90 degrees, while the fourth image I4 represents a phase angle of 270 degrees. By repeating these integrations during a given exposure time, a sufficient amount of light can be captured to obtain a better signal. Finally, a sine curve is fitted into the measured values in the images I1 to I4 for each pixel. This sine curve provides the phase angle phi, the amplitude A emission, and the constant component B emission, which are used to determine the corresponding fluorescence lifetime values. These lifetime images extend the information obtained by common intensity images. The reconstruction of the emission signal by means of half-wave integration requires a fast modulatable image sensor. This is where the modulatable high-frequency sensor FLIM2 comes into play. It was developed by CSEM and PCO from 2007 to 2012. In this unique image sensor, each of the 1008 times 1008 pixels has two charge collection areas, tap A and tap B. An externally applied two-level modulation signal controls whether the generated charge carriers pass through tap A or tap B. By modulating the excitation light and the image sensor at the same frequency, specific phase shifts can be measured in each pixel. At phase 0, tap A is active. All charge carriers are collected in charge bucket A. This is image I1. At phase 180, tap B is active, and all charge carriers go to charge bucket B, resulting in image I3. This kind of charge swing enables the simultaneous record of I1 and I3 in the same camera exposure, creating a double image. The image sensor modulation is shifted relative to the excitation light. Then, a measurement is performed at a phase angle of 90 degrees. The charge carriers collected in tap A create image I2. Tap B samples the information at a phase angle of 270 degrees, creating image I4. At a maximum modulation frequency of 40 MHz, minimum half-period integration intervals of 12.5 nanoseconds can be achieved. So this is what makes the PCO FLIM camera a versatile frequency domain FLIM system. It can be used for the measurements of a huge range of luminescence lifetimes from tenths of microseconds down to 100 picoseconds. The PCO frequency domain FLIM system is best in its class because it covers the largest range of lifetimes from tenths of microseconds up to hundreds of picoseconds. It's easy to apply, it has the highest resolution and the highest frame rate of the available FLIM systems at the moment, and its price performance is hard to beat. PCO FLIM is the perfect FLIM system for fluorescence lifetime imaging. FRET measurements, dynamic live cell experiments, optical chemical measurements like optical oxygen measurements, and more. For more information, please visit www.pco.de.
Now you've learned about the differences of time and frequency domain camera-based fluorescence lifetime imaging. You've seen that we achieved to develop a new CMOS image sensor, FLIM2, which has been used to create the camera system PCO FLIM. Since within this hands-on session, we would like to measure nanosecond lifetimes, which are the result of a FRET reaction, we have created the experimental setup on this table. Like for usual fluorescence measurement, we have a fluorescence microscope, in this case an inverse one, to which our camera system, the PCO FLIM, is connected. You see it here. The very convenient thing of the PCO FLIM is that all the modulation and frequency signals that are necessary are generated within the camera, so you don't need any extra instrument. At the moment, it's additionally water-cooled, but this is only required if the ambient temperature is above 25 degrees. In our situation here, it just makes the job for the inbuilt fan a little bit easier. The camera is connected with the modulation and the dark gate signal to the light source. Since we are going for nanosecond lifetimes, we are using today a laser for the wide field illumination of the microscope. The laser itself is coupled into a liquid light guide, while the light has to pass a diffuser to reduce the amount of speckles that would be caused by the coherent light of the laser. With this setup, that's all you need to do nanosecond lifetime images. One of the first questions scientists and customers always ask if they want to measure fluorescence lifetimes with a PCL Flim system is, which is the appropriate modulation frequency for a certain lifetime range? Well, regarding some mathematics, there is finally a very simple result, which is marked down there in yellow, and if I focus on that, you see it's a relatively simple formula. For a given lifetime range, the optimal modulation frequency equals 1 divided by 2 times pi and the square root of both lifetimes. And if only, let's say, a first single lifetime is known, then the formula is even more simple. It's just modulation frequency equals to 1 over 2 times pi and the lifetime. But this is just the suggestion for the optimal modulation frequency. Even if the modulation frequency that can be adjusted by the camera is a little bit lower than that, then still you can successfully and precisely measure lifetimes. The second question is, what is the appropriate light source? Since nowadays it's very popular to use light-emitting diodes because they are relatively cheap and powerful regarding their light output. We have to use a light source that can be modulated as fast as we need. So the situation is as such. We would like to continuously modulate the light source, and what is wished is a modulation depth that is near to 100%. This would be the light output in the left of these two graphs. Unfortunately, if you test LEDs and if you increase the frequency with which you would like to modulate them above 10-20 megahertz, then the modulation depth decreases. And we also have checked LED light sources that proclaimed to be modulatable up to 200 megahertz, but then the modulation depth is minimum. The problem with this is that most of the light, if you have a light source that has such a poor modulation depth, is wasted. It just burns and bleaches the samples without getting any useful information. Therefore, we suggest, if you have to measure fluorescence lifetimes in the nanosecond range, then modulation frequencies between 20 to 40 megahertz are required, and for that purpose only lasers are an adequate excitation light source. Below that, if you have lifetimes in the range of, let's say, 10 to 100 nanoseconds, or even in the microsecond range, then you very efficiently can use LEDs as light sources. I would like to introduce to you the PCL Flimpad, which is the control pad that allows the use of the PCL Flim camera system. It has 4 tabs. First one being called sequence configuration, which allows all the control parameters to adjust the camera system. At the very top you find the exposure time window, where you can select from a drop-down list the appropriate exposure time, and you can as well input it with the keyboard. This is followed by the modulation properties, which include the selection of the modulation source, internal or external, the selection of the output waveform, which could be either sine wave or square wave, and the input and control of the modulation frequency called master frequency. This could be in the range of 5 kHz up to 40 MHz. Then the phase sequence configuration has to be adjusted, which involves the number of phase samples that should be taken. Could be either 4, 8 or 16. Shiftable pair is just for rapid lifetime determination because it involves only a 2-tab readout. The additional phase sampling takes care of the asymmetry correction, which is required to reduce the amount of asymmetry noise caused by slight asymmetries between the 2 tabs in each pixel. The phase order, is only valid if additional phase sampling is set on yes, because this controls the sequence in which the inverse phase samples are taken. So either one total sequence after the other, or one double image and the inverse double image directly after the first one. This might help in case of strongly bleaching fluorophores to prevent any systematic error. The tab select button allows for selection of reading out either only one or the other tab or both, which is the usual case. The sequence configuration tab is followed by the referencing. The referencing describes the reference or the reference measurement, where you can adjust the number of images to average. You have to input a proper referencing lifetime, which I will show later on how to do that with a real reference measurement. Then you can capture the reference, you can save it, but as well you can load a reference file. If you've done this in the morning and you have the same settings again, then you can load the reference file and apply the reference to the current measurement. This is the referencing tab. The next one is called background correction, and this causes the camera, in case the setting is in a way that no light is reaching the camera, it causes the camera to record a stack of images that will be averaged and taken into account the behavior of the dark current. So there are a few different exposure times, very short ones and a long one, and the data are stored, and depending on the adjusted exposure time, this specific part of the offset is subtracted. Finally, there's the FLIM analysis tab. Here there are some controls how the phasor plot feedback is performed on the fluorescence intensity image, and you can have a look if the false color-coded result images should be weighted with the intensity distribution of the fluorescence intensity images. And that's about it. These are all the functions of the PCL Flimpad.
Before we can start with the real measurement, we need to perform a reference measurement, because this is required to figure out what is within your optical system. Keep in mind that in 1 nanosecond, light travels about 30 centimeters. And any additional 30 centimeters, therefore, would cause an additional phase angle due to this time delay. Therefore, we have to figure out what the system causes as offset, and for this purpose, we need a reference measurement. What is required for the measurement itself is a fluorophore with a more or less mono-exponential decay and with a known lifetime. It doesn't matter whether the fluorophore is dissolved in a plastic or it's a liquid, as long as you know the lifetime and as long as it can be used within the same spectral conditions like your sample. For our purpose, we are using these reference standards from a company named Stana Scientific in England, which are very convenient because the fluorophores are inbuilt within a plastic window, and we can use these metal slides which have the same size like a standard glass slide. With the adjusted camera controls, with all the settings that you need for your later on measurement, you make this measurement while placing the reference on the stage, switching on the light, covering it, and then focusing the microscope to the surface of that slide. And when you're ready with the focusing, you can switch to the camera and continue with the rest of the measurement within the software, which is in our case Nikon NIS Elements that controls the whole system.
Now I've focused on the surface of the reference slide and I'm switching to the camera readout and have a look to the live image. Here you see the structure of the dirt or some scratches on this reference slide on the surface. With that I can control whether it's properly focused, and then I move the slide to a position where there are less scratches. If I'm okay with the position, I stop live view and press capture with the settings that I've taken before. This is how it looks like if there's no reference present. So there are 3 result images of the sequence. One is on the upper left, the fluorescence intensity, then the phase angle distribution, and the modulation index distribution. The interesting parameter right now is to have a look to the mean fluorescence intensity, because here you see in the ROI statistics that the mean value is about 0.34, which means 34% signal. Now the exposure time for the reference measurement has to be adjusted in a range between 68 to 72% signal. Since I'm at 60 milliseconds, I double the exposure time. And take another measurement. Now you see in the statistics that the mean intensity is around 65%, which is pretty near to the value I would like to reach. So I further increase the exposure time to 125 milliseconds. And this looks pretty good. So the mean intensity is around 67, 68, that's okay. Now I can start the reference measurement, switch to the reference tab. I have to input reference lifetime, which I know from different measurements is 3.7 nanoseconds. And I press capture reference. Now the software separates the maximum exposure time of 125 milliseconds into a variety of different exposure times to cover the whole range of intensity, to acquire all the necessary measurements to do the corrections that are necessary to compensate the signal of the sensor. When the reference measurement is ready, it's always a good idea to store and save the results. And I'm always using different parameters for the file names to have a better identification of what I've done. Therefore, I have here the excitation wavelength, the filter and the objective modulation frequency and the sequence parameters. Since I now have referenced, I usually, for checking if the reference was okay or if there hasn't been any problems, I reduce the signal to 1/10 and do another capture. You will now see that the number of result images has changed, because since the reference was successful, now it is possible to convert the phase angle and the modulation index distributions into phase lifetime distributions and modulation lifetime distributions. To get a better impression if this reference was successful, I'm switching to the FLIM analysis tab, and I have a look to the phasor plot. Here you see the signal distribution in the phasor plot. It should be centered around 3.7 nanosecond, and if the reference was successful, it should have a circular shape because of the signal to noise behavior of the results. Then you might want to have a look at a little larger signal, because then at 20 milliseconds I would expect now with the next measurement that the circle of the noise around these 3.7 nanosecond becomes smaller, which is the result. So this looks like a good reference measurement, and now with this reference measurement you can take as many real data measurements as you like.
Now we've done a successful referencing, and we can start with the measurements. For this hands-on session, we've received some samples from a Spanish company named Fast-Base Solutions, which collaborates with Professor Benefshi Larijani from the University of Bath in England. They use kind of a biosensor made out of a FRET pair, which uses Atto 488 and Alexa 594 to mark and identify clear cell renal cell carcinoma cells. Therefore, we received a couple of slides with tissue slices which have been treated with their type of biosensor. And the procedure how to do a measurement is very similar to the reference measurement. So you place this sample on your microscope, cover it, switch on the light, have a look, focus, and then select any area of interest to do the measurement. And when you figured out the right spot, then the same procedure is you switch to the camera and have a look with the software, maybe refocus, and do your measurement.
Now, since I've identified a spot in the sample I would like to measure and investigate, I switch to the camera and have a look with Find whether the focus is okay. I can adjust. And if I'm happy, I stop and do a capture. So this is the whole measurement. Now, there are a few different ways of looking at the sample and investigating it. First of all, I show a phasor plot as additional tool. And then, if I'm having a first look to the sample, I might turn the focus to intensity and display only the intensity distribution. So this is the fluorescence intensity of the sample in the spectral range that I'm able to see with my filter cube combination. Now the corresponding phase lifetime distribution in false color coding in the range of 1.2 nanosecond to 2.6 nanoseconds is given here. And if I would like to access the values, I just point the cursor to any spot, like here, for example, this purple spot gives us a lifetime of 930 picosecond or 1.2, very short, so that's a patch. Or if I move over here to the purple section, it's around 1 nanosecond.
while the yellowish, reddish parts like here are above 2 nanoseconds. If I want to get more information about how this is linked to the structure, I can use this switch called intensity modulated display, and it will immediately give the color distribution of this false color image an intensity weight defined by the fluorescence intensity. With this, I can get a good overview where the short and long lifetimes are in my sample. Another possibility would be to use the phasor plot feedback. To explain what the phasor plot feedback can do, I'll switch back to display of all result images and then introduce to you the minimum intensity level that can be defined within the phasor plot. If I increase that level, any pixel having an intensity value that is smaller than the level is not displayed. So, say from 6% on, patches in the result images turn into black because all of these pixels have calculated from intensity values smaller than 7%. Another possibility with this phasor plot is the feedback of these values in the phasor plot itself, which are given by the combination of the pixel values of modulation index and phase angle, because both of these values define a vector where the distance to the origin is defined by the modulation index and the angle towards the x-axis is the phase angle. The parameter on the unity circle is the lifetime. If I'm interested in where in my original image are the structures or pixel values with a short lifetime, I can do the following. I put the focus on intensity, just display intensity. Then I open a blue circle, which I can change in size and position, and move it towards the short lifetimes. And if the intensity channel colors are highlighted, which I forgot before, now the corresponding pixels are painted in blue. All the pixels are painted blue that are within that circle. If I adjust the size of the circle, these are all the cells or structures that have a short fluorescence lifetime. Compared to that, the very long lifetimes, I could use, for example, red as a color and use the red circle as a probe. So these are all the structures and cells in red. That's another possibility of using very efficiently the phasor plot for feedback towards the original intensity image.
Now we've done the first measurement, and you could either continue investigating and exploring your sample or simply exchange the sample with the next sample and proceed like before, focusing, orienting, and then switch to the camera to continue the measurements.
But it's also possible to switch to a different slide to focus on a different sample. Have a look to the focus. Adjust the focus. Here we are in a range of more or less single cells. And do a capture. Again, a different range of cells. Let's have a look to the phase lifetime. That's in the range of 1.75 nanosecond up to 3.2. So that's a little bit longer lifetimes compared to the experiment before. Can adjust the scale a little bit to 3 nanoseconds. So these are all longer lifetimes. As well, this can be seen in the phasor plot by the histogram has moved towards
the range between 2 nanosecond and 3 nanosecond. Now you've seen how to do FLIM measurements with the PCL FLIM system. You could continue with the same settings now to investigate and explore more samples and do all the experiments you like to do. You will not have to repeat the reference measurement unless you are changing the spectral conditions, you are changing the objective, or you change the laser power, or you have switched off the camera. Then you will have to redo the reference measurement. If you want to be sure at the end of the day you could repeat a reference measurement to see whether things have changed, but usually that's not necessary. The data are stored within the Nikon environment as ND2 files as suggested by NIS Elements. If you want to process the result images with your own software or the different software packages, it's also possible to store the 5 result images within a TIFF file format. But you have to pay attention that now these images are result images. Therefore, the TIFF file does not represent a distribution of brightness, but values. So TIFF is used as container such that MATLAB or ImageJ can open the files, but then you have the real values. For example, in a lifetime distribution, a pixel value is not 100 count, but for example, 1.9 nanosecond. We think this is convenient to use further the files for further evaluation and calculations. We've come to the end of the hands-on session. Hopefully you could see how relatively easy and simple it is to do FLIM imaging with our PCO FLIM system. And it doesn't matter whether you are going for nanosecond or microsecond lifetimes, it's as easy. If you have applications that could benefit from this measuring technique, why don't you talk to my colleagues and arrange a test or a demo? Thank you very much for your attention.